All right, we are ready for lesson 2.1, part 2. There's just a little bit left. I'm sorry for the interruption in here, but we'll cover these last two slides that I want to cover, and that will take care of lesson 2.1. Okay, our idea here is a one-sided limit, and then we're going to compare that with a two-sided limit. What we've been doing so far have been two-sided limits because we're approaching a value and we're looking at both sides. Now we're going to do a one-sided limit, and on a one-sided limit, we're going to approach our value, but only from one side. So if you look carefully at this notation, it's still the limit as x approaches c, but the little plus means you've got values that are larger than c. So you could also say that's from the right side, or a right-handed limit. So the plus means values larger than c. Or we call that a right-hand limit. And then no big surprise here, with a little minus sign, we'll call this a left-hand limit. We're taking values that are smaller than c. Notice we never equal c because we talked about limits. We're getting closer and closer, and you never really have to get there. A nice example where we can contrast the left-handed and the right-handed limits are these one-sided limits. Is a greatest integer function. And I've got it abbreviated here with intx. Another notation that you'll see is two horizontal lines like this. And just as a review, the greatest integer function, that's kind of its short name. Its full name is the greatest integer less than or equal to whatever you put in there. So if I take the greatest integer function on 3, I get 3, because the greatest integer less than or equal to 3 is 3. If I take 3.1, the greatest integer function of 3.1, the greatest integer less than or equal to 3.1 is still 3. If I go 3.9, it's still 3. And it won't jump up to 4 until I get to 4. Where it gets slightly tricky are for negative values. So the greatest integer of negative 1.7, think about that, one more line. The greatest integer of negative 1.7, let's say the greatest integer less than or equal to negative 1.7 is negative 2. So occasionally people think the greatest integer function just truncates, and it's not truncating. Clearly on this one, this greatest integer of negative 1.7, is taking the greatest integer less than or equal to negative 2. When we look at the graph of the greatest integer function, it gives us a nice example where a left-handed limit and a right-hand limit can give you two different values. If you also refer to your book, that's in there as well. So let's take a look at the graph of this. We'll pull up a calculator. Bring that onto the screen for you. And the greatest integer function, we're going to go to our graph, we're going to go to y equals. And you can find the greatest integer function in the math menu and come over to number. And then it's number 5, this int. People get confused sometimes. They think it's the third one, the I part, but that truly does truncate. Whereas this int function is what we're looking for. The greatest integer function, I'll choose 5. Oops, close my clear. I'll choose 5. So I've got integer of x. Let's make a graph. Again, I prefer zoom decimal. And here's my greatest integer function. You can't see it, but part of the function that's on the x-axis also goes right there. And if we think about this, we'd have an open circle on 1 and a closed circle on 0. And similar, we have a closed circle and an open circle, a closed circle and an open circle throughout the whole graph. So give that a little bit of thought. But that should make sense. I'll try to improve on that calculator picture a little bit. Okay, so now in this graph, let's take the limit and let's have x approach to, we'll put a plus, so they're always bigger than 2. So if you think about this, we're treating values like 2.1, 2.01. Or if you look at the graph, here's 2. We're approaching it from the right side. So always bigger than 2. I'm looking at the function value, and it looks like the limit as x approaches 2 from the right is 2. Contrast that with the limit as x approaches 2 from the left. Now I'm always putting values less than 2, 1.9, 1.99. So I'm approaching 2 from the right. I look at my function values. They are consistently 1. So this gives us a nice example when you're approaching integer values of a function, the greatest integer function, where the left-hand limit and the right-hand limit are different. And again, note that's only for integer function. If I'm approaching 1.5, it doesn't matter what side I'm approaching 1.5 from. That limit will be the same. When I'm approaching integer values, the left-hand limit and the right-hand limit will give me 2 different values. So let's just save that graph. So we have that example. And then just understand this one little fact down here. See if this makes some sense. If a limit is going to exist, then the left-hand limit, the right-hand limit have to exist, and they better be the same value. Because that's what we're doing all along. When we're taking limits, we're approaching it from both sides. So just another kind of a clarification, a little detail here. You've got a left-hand limit, a right-hand limit. If your limit is going to exist, they both values, the left-hand limit and the right-hand limit, have to be the same. All right, last slide for this section. Always the focus in calculus is going to be on your multiple representations. Can you understand calculus when it's given to you analytically? Can you solve problems analytically? Can you solve them graphically? Can you solve them given a table? So here's a nice problem. They're giving us a graph of a function. They're going to ask us all sorts of questions about the limit. So instead of giving us a function, they're giving us a graph. I don't think we'll have too much trouble with this. Let's take part A here. We're going to take the limit. X is approaching, and look carefully, that's -1 from the right. And this is true or false. So I'm approaching -1 from the right side. Does my limit value equal 1? We look at the graph. We'll label that true. Part B now. Let's take the limit as x approaches 2. Notice this limit as x approaches 2, so we have to approach it from both sides. And it says the limit does not exist. Let's see. From the left side, I've got a value. From the right side, I've got a value. Those are the same value. They're 1. So this limit does exist. So we'll label that problem false. You might be confused because the limit is different than the function. But we're taking a limit, and we're not concerned about the dot up here. We're concerned about the left and the right, and those give us the same value. All right. And here's part C. The limit as x approaches 2. F of x is 2. No, it's not. It's 1. We just talked about that. The function value is 2. But the limit, we never get to 2. So the limit, again, if we look down here, that limit is 1. All right, part D. The limit as x approaches 1 from the left. So from the left, we're smaller than 1. X is approaching 1. We're from the left. And as we look at that y value, the function value, it looks like 2. We'll label that true. Part E, limit as x approaches 1 from the right. Now we're over here on this right side. Look at the function values. That is 1. We've got a true. Coming over here now to part F. The limit as x approaches 1 does not exist. That was the slide that we just had. For a limit to exist, the left-hand limit, that was part D, the right-hand limit, that was part E, they have to be the same. They're not the same. The first was 2, the second was 1, so it is true that the limit does not exist as we approach 1, because from the left side, we get 2, the right side, we get 1. Those are different values. Part G. The limit as x approaches 0 from the right. So let's come at 0 from the right. Let's come at 0 from the left. Do we get the same value from the left and the right? We sure do. That is true. And a couple more here. The limit as x approaches c for the function. So this is just any c. This limit exists at every c in the open interval from -1 to 1. Again, it's important to notice here it's an open interval, so we're not including -1 or 1. So we look from -1 to 1, and we're looking for spots where if I approach from the left or the right, the limit values would be different. There are no jumps in the graph. There are no asymptotes in the graph. That limit would exist at every single point between -1 and 1. Let's contrast that with our final problem, letter I here. The limit as x approaches c exists at every c from 1 to 3. And again, it's an open interval. And I apologize, that's not going to be a contrast. Let's look from 1 to 3. And so in here, any value in here, it sure looks like the limit exists. And the limit's going to be 1. Bigger than 2, between 2 and 3. Any of those values exist. And you might be worried about 2. Don't worry about 2. We've answered that already. The limit as x approaches 2 of f of x, that also exists. Because when we said it does not exist, we labeled that false. So the limit as we approach 2 also exists. So every c from 1 to 3, open intervals, those limits exist. So we're going to mark that one as true as well. And it looks like on this graph, if you consider the open interval from -1 to 3, the one spot where our limit does not exist was at x equals 1. So the last two questions, H and I kind of cleverly avoided the one spot where the limit does not exist. All right, that is the conclusion of lesson 2.1. Does anybody have any questions?